Hello everyone and welcome to another edition of Physics Friday. And as per usual here, I'd like to start off with a question. I have 2 points. I have point A and I have point B. And if I were to roll a ball down some sort of path between these points, which path would make it to point B the fastest? That is to say, which one's going to minimize the amount of time taken traveling from point A to point B. And the way we're going to do this is taking a look at Lagrangian mechanics. But first, what we're going to do is actually just take a look at the energy that this little ball, or particle really, carries as it rolls from point A. Oh goodness, I should have that on the curve. The energy this ball carries as it travels from point A to point B. So, initially, we're not giving this ball like a shove or anything. So initially, its kinetic energy is just flat out zero. But its gravitational potential energy, because we aren't necessarily starting from the origin, although it does make some things simpler later on, but that's not the point. The point is that we're dropping this originally from some point y naught, meaning that our gravitational potential energy is just going to be mg y naught. That's its energy at the point there. But say we take the ball to be at some different point. Say, I don't know, right here on this curve. Even though it's not the fastest, still a possibility it could, go through there. So we have our ball here, which has somehow grown. I might want to rethink the laws of physics for that. But the point is that its gravitational potential energy is now mgy, where y is really just our function connecting point A and point B. It's just the y value of that. But it's moving now, isn't it? It's not just gonna go and all of a sudden just stop. We're gonna have an extra term. So at this point, we have our gravitational potential energy, but we also have our kinetic energy, which is just 1/2 mv squared, where our velocity is just, tangent to whatever the curve may be. And as such, we know that our energy, must be conserved. So we have mg y naught is equal to mgy plus, scoop this over, plus 1/2 mv squared. So this is our conservation of energy, it shows the conservation of energy, or at least uses it. But before I go any farther in kind of exploiting this, I would actually like to go into what we're actually trying to minimize and manipulate that a bit so that we can actually apply what we've just derived here. So, off on a tangent, would recommend watching that video, but this is Physics Friday. Anyway, so what we're trying to minimize here, so minimize, if I can spell minimize, we're trying to minimize time. Yet one way we can express time is, say, an integral over dt, where basically we're finding the amount of time it takes over each little, say, interval here. I'm not going to draw that. I'm going to assume you are familiar with integrals a little bit. But one way we can express dt, right? So dt is, ds over dt. And now this looks incredibly silly because, couldn't you say, just move that up to the top and cancel these? And the answer is, mathematically speaking, that might be a little bit sketch, but yeah, essentially. But the reason we're writing it like this is because we need to note one thing. What is this ds dt? If s is just the curve that we're actually traveling along, or at least a little piece of it, if we're talking about ds, if that's just a little piece of our curve, then if we're taking the derivative of that with respect to time, then that right there is just our velocity of our particle along that curve. Meaning that one way to express dt, and therefore this integral, is just the integral of ds over our velocity v. And now you might notice a couple of things. By applying the conservation of energy, we know that, we can find our velocity in terms of our position, or at least our height, or the function of our curve y. And I'm going to come back to this ds term in just 1 second. But let's just sub in this v term right here, or really just solve for v real quick and sub it in. So this really isn't too bad because the m's all cancel. We don't really care about mass. So what we end up getting is v squared is equal to 2g, I'll just factor out the 2g, y naught minus y, meaning that our actual velocity is equal to 2g y naught minus y, and that's all in a square root. So subbing this in over here, what we have is actually the time, the thing we want to minimize, is the integral of ds over the square root of 2g times y naught minus y. But what is ds exactly? You might remember this if you've taken Calc BC or Calc 2 or something of the sort. But one way we can express ds, one of the ways ds is actually used is whenever we're referring to arc length, which is exactly what we are referring to here. So we can sub that in. But aside from just kind of pulling that from like Calc BC, Calc BC or Calc 2, you can think of this as a little piece of our arc length. So you could say this is essentially like dx squared plus dy squared, which if you factor out a dx, well, I say factor out, again, mathematically kind of sketchy, but I haven't taken real analysis yet. I need to get around to do that. Anyways, that's besides the point. If you quote-unquote factor out a dx, you get 1 plus dy over dx squared, and then a dx out front, meaning that our integral here, or what we're trying to minimize, is really just an integral of square root of 1 plus, I'm going to use the y prime notation, makes things a lot simpler, of y prime squared dx, all divided by square root of y naught minus y, and I'm just going to put the 1 over square root of 2g out front because it is just a constant you can throw outside the integral. And it's going to get cancelled out anyway, so it doesn't really matter all too much. So, that's all a lot, but we now have an integral of some function y with respect to x, and essentially what we can do here is apply the Euler-Lagrange equations, because this is basically our Lagrangian right here. And as such, I can just apply the Euler-Lagrange equation. Now, I'm not actually going to apply the full thing as you might find on Wikipedia, because that gets incredibly ugly and the algebra is, it's terrible. So instead, what I'm going to use is a slightly more simplified form of the Euler-Lagrange equations, and that's just assuming, or sorry, not assuming, we're saying given no explicit x dependence. So we're basically saying since there's no like x in here, there's no x there that's explicit. It's all implicit in the y. Because of that, we can rewrite the Euler-Lagrange equations in a different form. So this different form that I have been rambling on about is our f. So this is our function f right here. F minus, in my notes I have z prime, and I'll explain what z is in a second. Z prime partial z prime f, and that's equal to just some constant a. Z here, this z term this is really just whatever function we're trying to find the minimum of, essentially, and then it's prime, so you take the derivative of it. But before I actually go into solving this, I actually just want to define off to the side in red, just to make everything kind of nice and neat. We're just going to say z is defined to be y naught minus y. And you'll notice actually that this doesn't change the top part of our integral because, well, if you take the derivative with respect to x here, you're going to get negative y, but then if you square it, the negative goes away, so it really doesn't matter. But anyway, this basically makes our actual Right, our integral right here that we're supposed to be minimizing. Integral of square root of 1 plus z prime squared dx over square root of z. And then we can just apply this right here. It's really not that bad, kind of surprisingly. So we have the square root of 1 plus z prime squared, because after all, this is just our f right here, over the square root of z, minus z prime times the partial derivative of f with respect to z prime, meaning that our square root of z is actually just a quote-unquote constant out front. So we have that, and then we just have to differentiate the square root, or that should not be a full derivative. We just got to differentiate square root of 1 plus z prime squared with respect to z prime. And this right here is just equal to some constant a. We don't really care what a is. Anyway, we just got to do this derivative right here, which I kind of draw a bracket, which isn't too bad. This is just z prime over the square root of 1 plus z prime squared. Just don't forget your chain rule there. But throwing that in, we have the square root of 1 plus z prime squared over the square root of z minus z prime squared, because we have two of them, one here and one here, over the square root of 1 plus z prime squared times the square root of z. And that is equal to a. And multiplying the top and bottom of this right here by 1 plus z prime squared over square root of 1 plus z prime squared, just to get a common denominator, we see something that's actually extremely helpful. So because this is a common denominator, I'm just going to move this over to the other side, because we kind of have to anyway. Might as well do it now. Or actually, sorry, I'm going to only move that bit over. You'll see. So a times the square root of 1 plus z prime squared is equal to, well, what is that equal to? This is all over the square root of z. But we have 1 plus z prime squared minus z prime squared. But that right there is just 1 over square root of z. This simplifies a whole lot, which is really nice. So now all we have to do is solve for z, and we'll find our curve that minimizes the time taken between these 2 points. So yeah, let's get cracking. I'm basically just gonna isolate z prime real quick, and then do separation of variables. So getting z prime on its own, we have 1 plus z prime squared is equal to 1 over a squared plus z. Yes, that is right. And then just subtracting and then just subtracting 1 from both sides, we obtain that z prime squared is equal to 1 over a squared z minus 1. And then if we take the square root, we find that z prime, a very large z, goodness me, z prime is equal to the square root of 1 over a squared z minus 1. Dividing that, getting all our z's on one side, we find that dz over the square root of 1 over a squared z minus 1 is equal to dx. This is coming up here. Multiplying the top and bottom by a square root of z, we obtain that a square root of z dz over the square root of, what's that? Yeah, 1 minus a squared z is equal to dx. And then we can take the integral of both sides. Oh, goodness me. We can take the integral of both sides. And I do apologize, so I'm just kind of breezing through this part of the video. This really just is ugly algebra. It's really nothing too exciting in my opinion, so. What is slightly more exciting though is a use of. We're going to let z equal, not a squared, pardon me, 1 over a squared sine squared theta. And this right here might seem a little bit weird why we'd want to do that, but the answer really just lies in the fact that This right here will simplify to just a cosine term, and the numerator will also just simplify to a normal sine term. And then, well, you'll see what dz is right now, actually. We shouldn't do that. Dz is just equal to 2 over a squared sine theta cos theta. Meaning that this cos theta here is going to cancel with the cos theta down there. We're just going to get a sine squared, essentially. So I'm just going to move that on over. And this just means that our integral is equal to x plus c. We can make the right side at least a little bit easy. And we still have our integral, but we have, I'm putting the 2 over a squared out front. We have our sine theta, cosine theta. And let's just focus on this a squared to z term. So if the square root of z is just going to be sine of theta over a, but we already have a right there, meaning the a's cancel, and we're just left with the sine theta. So the sine theta on the numerator is actually just squared, d theta, of course, and then over, well, the square root of 1 minus a squared z. Well, the a's here are going to cancel, leaving us with just the square root of 1 minus sine squared, which is just cosine. Meaning those cancel, leaving us with 2 over a squared times the integral of sine squared theta d theta. And now this integral really isn't that bad, so long as we use the little identity here. 2 sine squared theta is equal to 1 minus cos 2 theta. Meaning, let me just scroll down. Meaning that we have 1 over a squared times the integral of 1 minus cos 2 theta. I just applied the 2 here. That's all I did. And now this really isn't bad to integrate at all. We just have a 1 over a squared times theta minus 1/2 sine 2 theta. But we are not done, because we did do a substitution, didn't we? We said that z was equal to 1 over a squared sine squared theta, meaning that our theta, that's like a cactus green, interesting. I haven't really used that marker in a while. Anyway, sorry. Our theta is actually just equal to inverse sine of a times the square root of z. And as such, we can plug this in and find that we have 1 over a squared. That thankfully does not change. Theta is just sine inverse of a square root of z. So nothing too crazy there. And then we have this really interesting term. And I'm going to kind of just deal with this off to the side before writing it in. Just I think it'd be a little bit helpful. So what we have essentially is a 1/2. We have a negative here. I'll just write that in. But what we have is a 1/2 times the sine of 2 times the inverse sine of basically a square root of z. And this looks quite ugly, in all honesty. But we can just apply, I believe it's a double identity. I forget the actual name, but just the fact that 2 sine theta cos theta is equal to sine 2. My recording little thing is in the way. Sine 2 theta. And as such, we can find that this right here is just our sine of 2 theta. Well, theta, quote unquote. This right here, well, the 2's are just going to cancel. So boop and boop. Meaning that we're left with sine of inverse sine of a times the square root of z. And then times the cosine of inverse sine, or arcsine, of a times the square root of z. And this is a lot nicer to evaluate, because this term right here is just going to be a times the square root of z. And this term on the right is just going to be the square root of 1 minus a squared z. So subbing that into our original equation, we find, if I can find my green marker again, this is just a square root of z times square root of 1 minus a squared z squared, or z, not z squared. So, one last substitution. This is a very long video, but that's okay. Earlier we did define z to be y naught minus y. Meaning, if we're actually trying to quote-unquote solve for y, or try to find some expression in terms of y, well, we need to sub that in. So subbing everything in, kind of like for the last time, what we find is, I'm going to scroll down. What we find is our x plus c is equal to 1 over a squared times arcsine or inverse sine of a times the square root of y naught minus y minus a square root of y naught minus y times the square root of 1 minus, oh goodness me, a squared y naught minus y. Oh goodness, this is a lot of stuff. And this really is, I'm gonna be honest, this really is not too nice. It's not very pretty. But if you actually visualize it with the Desmos, I have linked in the description. Quick 21-minute plug there. If you made it to 21 minutes, congratulations. Congratulations. That's an accomplishment. I don't know how you have that much patience. But anyways, yes, Desmos is linked down in the description. But the shape of this right here is actually just a cycloid. Which is quite interesting. A cycloid is really just, so if I'm going to draw this here, a cycloid is basically if we were to basically draw a circle here and say it's going to rotate, it's going to roll this way. And essentially what the cycloid is if we get like one point on the circle and we just track it as the circle moves. So essentially what's going to do is go like, ooh, boing, boing, boing. Basically that, but since this is the Brachistochrone, it's actually going to be a shape that looks more like this for points there, or for points more over here, it's going to look more like this. If I can actually hit the point. I'm just going to move the point. Anyways, that is the equation for the Brachistochrone, and this is how we minimize the time between 2 points A and B. And this video has officially taken the prize, if it can be considered a prize, for the longest on this channel, which for better or for worse it is. Anyways, I hope all of y'all enjoyed, and I hope y'all also especially enjoyed the Desmos in the description. And I'll see y'all not next Friday for Physics Friday, because that's a push. So the week after next Friday. See y'all then for Physics Friday. Anyway, thank you for watching.